Welcome back for our next discussion in Chapter 8, where we're going to be going through our new technique of integration, which is going to be trigonometric substitution. So another technique available to us that we're going to introduce today and work with is going to be replacing algebraic expressions by trig functions. If you remember in the previous videos, we discussed evaluating trigonometric integrals. And the reason being is because now what we're going to do is we're going to take algebraic functions, non-trig functions, convert them into trig functions, and therefore have to evaluate trigonometric integrals. So we introduced, reminded ourselves, discussed trigonometric integrals in the last two videos, and now we're going to put that to practice in the technique, the new technique of integration called trigonometric substitution. And so before we get started, I'm just going to remind us of some of our Pythagorean identities. These are the three that are going to be useful. The Pythagorean identity solved for sine squared, the Pythagorean identity solved for secant squared, and solved for tangent squared. So if you remember the last discussions, we wrote down our Pythagorean identity and the variations of it. These are the three that are going to be useful. They're going to give us the framework for substitution. So sine squared is 1 minus cosine squared. Secant squared can be written as tangent squared plus 1. And tangent squared can be written as secant squared minus 1. And why do we only look at these three? Because these three trig identities gives us a way to relate sums and differences of squares. If you look here, we have a difference of squares. 1 squared minus cosine squared. We don't write the square on the 1, but we can assume it's squared. 1 squared minus cosine squared, a difference of squares where the constant is first, can be rewritten as sine squared. 1 minus cosine squared is sine squared. A single expression. Here, a sum of squares. Tangent squared plus 1 squared. This sum of trig things, this trigonometric sum of squares, can be replaced by a single expression, secant squared. And likewise, another difference of squares, where now in this case the constant is second, secant squared minus 1 squared, or secant squared minus 1, can be replaced by a single trigonometric expression, tangent squared. And so these versions of our trig identities is kind of a way to address sums and differences of squares, and very specific squares of trig functions, where one of them is constant, and replacing that sum or difference by a single trig expression. Now, why do we have two cases for differences? That's important when we talk about differences of squares. Since subtraction is what we call in math non-commutative, meaning if you subtract in the wrong order or a different order, it's not the same answer. 3 minus 2 is not the same as 2 minus 3. They are different numbers. Addition is commutative. 3 plus 2 and 2 plus 3 are the same number, but subtraction is not. You learned this at the beginning of Chapter 7 when you talked about applications of integration and volume and all that fun stuff. It became very important which way you subtracted, bigger minus smaller. In the same way, since subtracting in a different order yields different numbers, we would have to have a different scenario for a difference of squares, right? One where the constant is first and one where the constant is second. Why do we bring this up? Well, in this section, we're going to be looking at certain types of algebraic expressions. So non-trig things right now. And we're going to be looking at specifically sums and differences of squares, where a is a constant. So say we have a difference of squares here, a squared minus x squared. Or a sum of squares here, x squared plus a squared. Or the other difference of squares, where now the constant is second, so x squared minus a squared. A is just some general constant. It could be 1, like here it's 1, but it could be 2 or 3, or the square root of 3 even, right? A doesn't have to be a whole number. It could be a fraction even. So sums and differences of squares. And not only that, we'll look specifically at underneath roots. And we'll talk about why roots become important. That's because a very basic algebraic principle is that roots do not break up over addition and subtraction. So we don't want to make the mistake of thinking that I can simplify this to a minus x. If that were the case, then we wouldn't need any sort of further technique and our integrals would be very easily solved. But in algebra, we learn that roots are like exponents. And exponents do not distribute over addition and subtraction. You have to FOIL and do all that kind of fun stuff. And so in the same way, roots do not. Roots do split up over multiplication and division. I can break a root up over a numerator and denominator or over a product, but I cannot distribute a root over addition or subtraction. So you can't do anything to simplify these expressions as they're written. And so we're not going to introduce calculus yet, we're just going to look at these algebraic expressions. And I'm going to relate these algebraic expressions to one of these three trigonometric expressions. So if we look at the right-hand side of these trig identities, we deal with sums or differences of squares, and we kind of want to match them up appropriately. You notice in the first one we have a difference of squares, so that's either going to be sine or secant. In this case, my apologies, we're actually going to use a different version. I wrote it down incorrectly at first. Although that's a true identity, the actual one we're going to be doing is the other version of it, that 1 minus sine squared is cosine squared, not 1 minus cosine squared is sine squared. Although the other identity is true and it's not incorrect, these three are the ones we want. And so if you go back to your Pythagorean identity, right, sine squared plus cosine squared is 1, we could have moved sine or cosine over by subtracting it. In this case, we're actually going to want to move the sine over. So my apologies, but 1 minus sine squared equals cosine squared. So we look at the difference of squares, or the constants first, it looks like 1 minus sine squared. If we look at the sum of squares, well, there's only one for sum, and that's tangent is the variable, or is the function, and the one's constant. So it kind of matches with this one. And the other difference of squares, where the constant is second, looks like it matches up with this one. And so what I'm going to do is just do a very basic substitution. So not integrations, we're not looking at differentials or anything like that. All I'm going to do is choose to replace x in all three of these scenarios by a trig function. In this case, I'm going to replace x with a sine of theta. Now, it's important that I put that a in front. In this case, I'm going to replace x with a tangent of theta. And in the last case, I'm going to replace x with a secant of theta. Why these specific ones? Well, these specific trig functions are in some way related to these sums and differences of squares, which are related to these specific Pythagorean identities. I couldn't choose a different trig function for this one. This is one that relates sine and subtraction of squares in this way, and so on. Now, it's important that I put the a in front because while these Pythagorean identities are great, it's very important that this can't be any number here. It has to be the number 1. And so in general, if we have a constant here, a, we may need to factor it out so that we can get a 1 there. And the only way I'm going to be able to do that is if I put an a squared here with this term so that I can factor it out. In doing so, we'll put an a in front of sine. So if I just do this substitution directly, so we'll do the substitution now. What this will now give me is, well, we still have a root. We still have a root. We still have a root. We'll get a squared. I'm not replacing anything with the constant. So those are all the same. All I'm doing is replacing the variable x by the trig function. Now, if I replace x with a sine of theta, don't forget we need to square it. This now becomes a squared sine squared. Right? We're squaring a sine of theta. And in this case, we're squaring x here. X is now a tangent, so now this becomes a squared tangent squared. And in the last one, we're replacing x with a secant of theta, giving me a squared secant squared. And now we see why I wanted to put an a in front of that substitution, that constant a, so that now in all three of these scenarios, I can factor the a squared out from each term. And not only that, we can actually factor it out of the root. So if I factor that out of the root, we're going to get an a in front. So factoring an a squared out from each term and pulling it out of the root, the square root of a squared giving me a, gives me 1 minus sine squared here. And now we see why we use this trig function to relate to this identity. And in the second one, we get tangent squared plus 1. Another identity. And in the last one, we get the last identity written up there, which is secant squared minus 1. So we've taken a sum and difference of squares algebraically and turned it into a very specific sum or difference of squares trigonometrically with a very specific trig function so that that sum or difference appropriately can now become a single trig expression. that 1 minus sine squared now just becomes cosine of theta, or cosine squared theta. The second one now becomes secant squared theta. The last one becomes tangent squared theta, using these identities. So now I use it, use what they're equal to in all three scenarios. And why do we have the root in general? Well, now that the double terms, or the two terms, have now become a single term, well, now we can actually take the square root. Right? The square root of cosine squared is now going to be cosine of theta. The square root of secant squared is now going to give me secant of theta. The square root of tangent squared is now going to give me tangent of theta. And so what have we done? Let's kind of fast forward the tape now. We've taken an algebraic expression, something in algebra that's kind of complicated, can't be simplified, and through a substitution, we replaced it by a single trig function. That expression purely becomes a cosine of theta. In the second case, this sum of squares underneath the root, complicated algebraic expression, becomes a simple trig function now. A single trig function, a secant of theta. And in the last one, this difference of squares underneath that root, a complicated algebraic expression, becomes a simple trig function, simply just a tangent of theta. Remember, a is just a number in front, right? So in all these scenarios, we're getting a single trig function as our answer, as our substitution. How did we get there? Well, of course, we had to obey some sort of substitution. We replaced x with a sine of theta in the first case. We replaced x with a tangent of theta in the second case, and with a secant of theta in the third case. Why do I pick those specific trig functions for those scenarios? Is because I want to get a very specific identity, the identity that matches here. So I need to pick the appropriate trig function. Now, that may seem complicated, but there's an easy way to remember the correct type of trigonometric substitution that you need to make. So if you remember, we're doing trig substitution. I'm going to give you a little shortcut here. Trig sub. If you look at trig sub, the first letter of trig is T, the first letter of sub is S. And if you think of all of your 6 trig functions, the only ones that start with the letter T or S are sine, secant, or tangent. No cos, no c's, no cosine, no cosecant, no cotangent. If we look at trig sub, we look at T and S, and we look at the 3 functions that start, the 3 trig functions that start with T or S, sine, secant, or tangent. This is an easy way to remember which substitutions you're going to want to use. So out of the 6, we're narrowing it down to 3, first of all. So sine, secant, or tangent. One of those 3. Now, which one is the correct one to use? So if we have an addition of squares, so a sum of squares, a plus sign between them, we look at tangent. Tangent, the first letter is T, which looks like a plus sign. So if we have a plus sign, a sum of squares, we will use tangent as our substitution. So sum of squares, my variable will replace by tangent, that trig function. So then what about a subtraction of squares? Well, subtraction starts with the letter S. Subtraction of squares, sine or secant. So either sine or secant when I have subtraction. Sine or secant when I have subtraction. How do I know which one? It all matters to where the constant is, where the number is. If the number is second, you will choose secant. The number is second, you choose secant. And now by process of elimination, that means that the number is first, you will choose sine for your variable substitution. So again, an easy way just kind of to go through and remember which trig function we want to use given the scenario that we have. If it's a plus sign, that looks like the letter T, and so my trig sub will be tangent. If it's a subtraction, then I'm either using sine or secant, and then it just matters where the number is. If the number is second, I choose secant, and if it's first, then I will use sine. So that just gives us kind of an easy way to remember. Now, before we move on and actually put this into practice, right, we haven't done any calculus yet, just some algebra and geometry and trigonometry. I'm going to kind of formulate these substitutions in terms of something else, in terms of a triangle. Because where else do we get our trig functions? We get them from right triangles. And so I'm going to give us three different types of right triangles that we're going to run into. Why do I do this? Because, well, it may help us when we rewrite answers to integrals and using trig substitution. We may want to draw a triangle maybe at some point, may help us. And so say we have a right triangle here and we have some angle theta. And so say we have two sides known to us. Say we have x here and a here. So the opposite side x and the hypotenuse some constant a. Then if we just relate these two sides, well, the relationship between this angle and the opposite and the hypotenuse would be a sine relationship, right? Sine is opposite over hypotenuse. So I know these three bits of information, I can relate them with sine. Specifically, sine of theta would be x over a. Rewritten, this would mean that x is a sine of theta, if I multiply both sides by a. Now the nice thing is, because of Pythagorean's theorem, Pythagorean identities, because of Pythagorean's theorem, anytime I have two sides of a right triangle, you always get the missing side, not for free, but you could do some work. A squared plus b squared equals c squared. So using Pythagorean's theorem, I can find this missing side. What is the missing side? I will do it in this case, and then we're going to see the pattern or what's going to end up happening. If I try to find that missing side, let's write it out. I get question mark squared plus x squared equals a squared. If I want to solve for the question mark, I would subtract the x squared to the other side, giving me a squared minus x squared. I would take the square root of both sides, giving me this expression. Wait a minute, that's funny because that's exactly the algebraic expression, that difference of squares that we started with here for that specific trig sub. And so what is the missing side? The square root of a squared minus x squared. So if I have this scenario set up for me, the relationship between this angle, the opposite and hypotenuse, giving me a sine relationship like this. What's the missing side? Well, it's this algebraic expression here. And then if I want to relate this algebraic expression with theta and that constant, right, we won't relate it with x, right, because, well, the constant is nice and only one function or one unknown part. Then the relationship between this angle, the adjacent side, and the hypotenuse would be a cosine relationship. In fact, in this case, we have cosine of theta would be adjacent over hypotenuse. And again, multiplying both sides by just that constant a gives me then that this algebraic expression is a cosine of theta. And that's exactly what we just showed, right? So if I just underline this part here, we just showed via algebraic substitution, hey, this algebraic expression, if I have this relationship, becomes this trig function. So again, this algebraic expression within this triangle, given this relationship, x equals a sine of theta, yields this trig function. And so we get this relationship geometrically as well. So that's where they come from as well. I'll do the same thing for the other one. So for example, say we had another right triangle, theta is the angle, and say we knew maybe not the hypotenuse this time, but maybe just the opposite and adjacent side. And so what would we get here? Well, that relationship between the angle and the opposite and adjacent side, that's a tangent relationship. So tangent of theta would be x over a. Or specifically, if I multiply both sides by a, x is a tangent of theta. So that's the relationship I have. So say I have a right triangle with this amount known to me, right? This relationship. If I have this relationship, well, the missing side, and if you use Pythagorean's theorem, which I won't again, but if you do, you're going to find out that the missing side of this right triangle is this algebraic expression. And sure enough, if I want to now relate this algebraic expression with theta and my constant, that would be a relationship between the hypotenuse and the adjacent side, which if I want my expression in the numerator, that would be a secant relationship. And so what is secant of theta? That would be hypotenuse over adjacent. And so if I multiply both sides by a, I get this algebraic expression then in this triangle yields a secant of theta, which is what we wanted to show. And so again, just to do the last one, just to show you geometrically, so you know that all of them are related in terms of a triangle. Say we have a right triangle again and an angle here. And say we have now not the opposite hypotenuse or the opposite adjacent, but maybe we have the hypotenuse and adjacent. So maybe we have something like this. Well, hypotenuse and adjacent, that's a cosine or secant relationship. In this case, since the hypotenuse, we're going to make the x, we'll have to put it in the numerator, make a secant relationship. Secant of theta is x over a, which implies, of course, that x is a secant of theta. Well, okay, well, what's the missing side of that triangle? If you use Pythagorean's theorem, promise, you will end up getting this algebraic expression. Square root of x squared minus a squared. Well, now we have this algebraic expression, and we want to relate it with theta and my constant. In that case, that is a tangent relationship, opposite and adjacent. And so what would this mean? This means that tangent of theta is square root of x squared minus a squared over a. Multiplying both sides by a tells me now that this relationship, this algebraic expression in this triangle is now a tangent of theta, which is what we wanted to show. Here. And so we're not doing something new. I'm just doing the same thing kind of twice over, once algebraically, so without looking at any sort of pictures, the other geometrically, looking at right triangles. And we see that they are very closely related, these algebraic expressions and these trigonometric identities and these trigonometric functions. And so this is kind of the setup or the framework for trigonometric substitution. And so what we're going to end up doing in the next video now is say, okay, well, now let's apply this to integration. Let's say we need to integrate something where I have an expression like this in my integration. I have an expression that is a sum or difference of squares, preferably under a root. If it's not the end of the world. We can still do trig sub, and we'll see that. So sums or differences of squares underneath roots. We are able to then do a trigonometric substitution to manipulate it, to change the way it looks, and take that algebraic expression and rewrite them as very specific trigonometric functions. And so in the next video, we'll now take this information and apply it to integration.